Well, this is what I set out to try and help achieve with the help of Professor Mariana Banea and her research team here at DEMAC and University of Aveiro. The main goal is to develop a sustainable alternative to the current composite solutions found in the UAV industry. The demand for unmanned aerial vehicles is in exponential growth. These vehicles, from massive fixed-wing military options to small hobby-grade quadcopters, almost always produce with carbon fiber composites. The main problem with this material is that the actual fibers are produced through extremely high energy demanding processes. The fossil fuel based raw precursors need to be kept at around 300 degrees Celsius for up to 2 hours. Then they need to be brought up to 1500 degrees Celsius. Furthermore, high performance fibers might also throw an up to 3000 degrees Celsius process into the mix. All these factors combined ramp up the pollution associated with the manufacturing of this material, which is especially worrying considering that composite materials are nearly impossible to recycle. What about replacing carbon with something natural? Flax fibers come from plant stalks, requiring much less energy to be turned into usable fibers. This, paired with them being less dense and fully biodegradable at the end of life, constitutes a very attractive option from an ecological standpoint. Their natural origin, however, makes them much weaker than carbon. So, to reduce the performance loss while sticking to the main goal, we started looking into hybridization. This is when stronger fibers, in this case carbon, are mixed with main fibers, in this case flax. Reinforcement fibers can be dispersed either throughout the toe, the weave, or the stack. The latter option is much easier to implement, so we went for two distinct configurations. One replaced both surfaces of the specimen with two carbon layers each, hybrid C2. The other replaced only one, hybrid C1, with the remainder being 6 or 7 layers of flax, respectively. All that remains is to bring this into practice and test the mechanical properties of the resulting unidirectional composites. The pure carbon one reached a flexural strength of 1601.67 megapascals, hybrid C2 reached 734.29, the C1 315.91, and the pure flex 217.68. When it comes to impact resistance, the pure carbon composite achieved 80.93 kilojoules per meter, the hybrid C2 1.87, the C1 3.42, and the pure flex 0.52. This means that when compared to its pure carbon counterpart, the C2 hybrid uses 71.4% less carbon, while retaining 45.8% of flexural strength and 20.9% of impact resistance, and the C1 uses 85.7% less carbon, while retaining 22.5% of flexural strength and 38.3% of impact resistance. This means that yes, sustainable solutions are viable despite the trade-offs.